So in quantum mechanics, Werner Heisenberg proposed a fundamental limit for how precisely we can know two conjugate variables such as position and momentum at the same time. Okay, so the mathematical statement of this uncertainty principle is delta x dot delta p greater than equal to h cut by 2. Here, the delta x equal to uncertainty in position or standard deviation in position, and delta p is uncertainty in momentum or standard deviation in momentum. Physical meaning of this equation is if a particle very localized in position, suppose in the range of delta x, okay, so its momentum is highly uncertain, that is delta p. So that means the standard deviation is large if you may measure the momentum. And if a particle's momentum is well defined, it must be spread out in that space. So that means the standard deviation is large if you measure the position. But you have to understand that this is not a limitation of measurement variables. It's a fundamental property of nature. It's deeply rooted, or the concept of this uncertainty originates from the wave particle duality in quantum mechanics, or you can say non-commuting operators in quantum mechanics. That's same. In this simulation, we model quantum particle using Gaussian wave function. But the question is, why Gaussian? In quantum mechanics, a wave packet can be described a free particle with some uncertainty in position and momentum. So this Gaussian wave packet is normalizable and analytically solvable, well behaved, smooth, it has a symmetry, and easy to transform between position and momentum space, only using Fourier transform. That's it. Fourier transform of a wave function connects the position space and momentum space. So here d delta x and d delta p, this pair is the best example for illustrating the uncertainty principle. Okay, so after assuming the Gaussian wave packet, next is we will vary the sigma, the standard deviation. So by adjusting the width sigma, the standard deviation, which is the width of that Gaussian wave packet, so it determines how spread out or how narrow the wave function is in the space. Okay, so smaller sigma means more localized particle, and larger sigma means more delocalized. Okay, so here we observe how localizing the particle in space causes its momentum spread to increase. Next, using a Fourier transform, we transition from position space to momentum space, and revealing the dual nature of the particle. Finally, we calculate and visualize the delta x and delta p and confirming the Heisenberg uncertainty principle. Basically, it's a numerically proof. Okay, so this is the basic. So now we understand all these steps which I am going to use in that code. So first, we consider a Gaussian wave packet in position space. Then we define our quantum system in position space. Let's say from -10 to +10. So this gives us a clear resolution of where the particle might be found. Second is we will choose different widths or different sigma to see how changing the spread in position affects the spread in momentum. So again, I am telling that a smaller sigma means more localized particle and larger sigma means more delocalized. Okay, now it's time for generate the wave function in position space. So we repeat this for different values of sigma, which controls how wide or narrow our wave function is in position space. So for each c sigma, we generate a Gaussian wave function representing the probability amplitude of finding the particle at position x. Now our next step is apply Fourier transform. To understand momentum, we have to perform Fourier transform. This mathematical tool converts our wave function from position space to momentum space. It shows us the distribution of momentum for our particle. Now, after having the different space wave functions and doing that Fourier transform, now it's time to calculate probability densities. So we compute probability density in both space, in position space and in momentum space, to see where the particle is most likely found. So after calculating the probability density, we measure the spread or the uncertainties. Okay, so we now compute the standard deviation of x and p and called as a delta x and delta p. These represent quantum uncertainties in position and momentum. And finally, the last step is compute the uncertainty product. So we multiply this delta x and delta p to check whether the result respects Heisenberg principle that their product is always greater than or equal to h cross by 2. So multiplying delta x and delta p gives us the uncertainty product, and this is where the beauty of the simulation shines. We find that for each Gaussian wave function, the product delta x dot delta p is always greater than or equal to h cross over 2, just as Heisenberg predicted. And at last, we plot the probability distribution and annotate them with the values of delta x and delta p. So we can visually confirm the uncertainty relationship. Okay, so this simulation not only shows Heisenberg's uncertainty principle but also helps us understand the deep link between Fourier analysis and quantum physics. So it provides a numerical laboratory where we can see and verify one of the most fundamental principles of quantum mechanics. We begin by importing two essential Python libraries. One is NumPy and another one is Matplotlib. Import NumPy as np and import matplotlib.pyplot as plt. So now h bar equal to 1. That Planck constant I am giving 1 for our simulation purpose or calculation purpose. Next, we will define our positional space x dot np dot line space, okay, minus 10 to plus 10, let's say, and divided into 1000 points. So here we define our positional space, a line from minus 10 to plus 10 and divided into 1000 points. So this gives us a fine resolution in position space. So next we have to define a function to generate Gaussian wave packet. So it's DEF, define Gaussian Gaussian wave packet, PACKET x sigma, which is a variable of x and sigma, that is standard deviation. Okay, so return bracket 1 divided by sigma into np dot square root 2 of 2 pi, 2 into np dot pi. So 1 by sigma root over 2 pi. Okay. Into exponential term. So np dot exp minus x square divided by 2 sigma square, 2 into sigma square. That's it. Okay, so we perfectly define our Gaussian wave packet function. So now it's time for defining a function of Fourier transform to get momentum space wave function. So def momentum, so def momentum wave function which has a variable of psi and psi x, sorry, which has a one variable that is psi x. So now I have to Fourier transform this positional wave function. So that means psi x, no, sorry, psi k in momentum space. Psi k equal to np dot Fourier transform fft dot fft shift np dot fft dot fft np dot fft dot ifft shift, which is a variable of psi x. Okay, so psi k is equal to Fourier transform of np fft shift psi x. Okay, done. So now I have to define the dk. So dk in momentum space is 2 into dk equal to 2 into pi np dot pi by the length of x in position space into dx. Okay, done, done. So now I have to define k. So k equal to np dot Fourier transform dot fft shift np dot fft dot fft frequency which have a length of x or positional coordinate length x and d equal to dx. That's it. Okay. So k equal to Fourier transform of that positional coordinate d equal to dx into 2 pi 2 into np dot pi. That's it, 2 pi. Okay, so we defined our Gaussian wave packet which is normalized. So then we define a momentum wave function which calculate the wave function in momentum space by Fourier transforming the positional space. है ना? Okay, so now it's time to normalize. For normalization, suppose p psi k equal to into equal to dx by square root 2 sqrt 2 np dot pi 2 pi. Okay, so it normalized. So now return k and psi k. So now we will run this simulation with three sigma values. One is small, medium and large. So sigmas equal to suppose 0.5, 1 and 2. Okay, now fig dot axis equal to plt dot subplots which is the length of sigmas which have two which have a fixed size equal to 10 along the x-axis and along the y-axis is 6. That's it. That's it. Now it's time to run this simulation using for loop. Okay, so here we are going to use for loop. So for I, oh sorry. So for I sigma in enumerate sigmas psi x equal to Gaussian wave packet which has a variable of x and sigma, I think. Okay, then k and psi k equal to momentum wave function which has a variable of psi x. Okay, now it's time to calculate the standard deviation. So first we calculate the standard deviation of positional space, then we calculate the standard deviation of momentum space, and then we multiply it to total uncertainty. So let's do it. So delta x equal to np dot sqrt square root 2 of np dot sum x square into absolute value of np dot absolute value of psi x square. So delta x equal to root over x square in absolute value of psi x okay into dx length of that positional coordinate. And then now delta delta p equal to in the same manner np dot is qrt in m dot sum. So now instead of x in momentum coordinate I'm using k. So k square, so k square into np dot absolute value of psi k, not x, because we are in momentum space, into psi k square, psi k square here into k of 1 minus k of 0. Okay, it's better to put it in bracket, so I'm using again one bracket extra. Okay, okay, ah right, right. So we calculated the delta x, delta p. Now total uncertainty. So uncertainty product equal to delta x into delta p. Okay, now print position uncertainty, which is in the delta x. Now momentum uncertainty, spelling mistake, certainty, which is in delta p. Now total uncertainty equal to uncertainty product, UCT. Okay. So if I run this code, if I have not done any mistakes, then it will calculate the sigma or delta x in positional uncertainty, and in momentum space that in delta p, that is momentum uncertainty, and it also calculate that total uncertainty. So let's see it will run or not. What happened? Name dx is not defined. Dx this one, this, okay, okay, silly mistake. So first I have to define our dx, which is x1, sorry, x1 minus x0. Now it will work, I hope. Yes, it works. So see, the position uncertainty is 0.26. Okay, 26556 for an example. So you can see it calculates for sigma equal to 0.5, sigma equal to 1, and sigma equal to 2. So for sigma equal to 0.5, the positional uncertainty is 0.26. Okay, for 1 it is 0.37, and for 2 it is 0.53. So it represents that increasing of sigma, the uncertainty of position is increasing. Okay, and in momentum space, the momentum uncertainty decreases. Okay, so for less positional uncertainty, you will get the maximum momentum uncertainty, that is 1.06. So the for large sigma, which is 2, so for large sigma which will affect in positional space, that position uncertainty is 0.53. Okay, but which is maximum. But in momentum space, for the same value of sigma, which is 2, uh, the momentum uncertainty is 0.13, which is less, just as the Heisenberg predicts. Okay, so now that numerical calculation satisfies this thing, but now we will plot this for our better understanding. First, we will plot the position space. So plot, sorry, axis I0 dot plot x np dot absolute value of psi x square, which is label equal to. So for labeling here, I am using some latex. So in Google Colab you can use latex very easily. Okay, so access, it can be same thing, I think, na? So access I0, I'm just copy pasting because I don't want any silly mistakes. Set y level, label level, the probability density. Okay, then x is I comma 0, set title, set title bracket. Again I am using some latex for our naming the title in positional space. Okay, so I think for position space I already done it. Access equal dot, just I have to just I have to give one command, and I0 dot legend dot legend, that's it. So if I run it, I will get, hopefully I will get, yes, yes, yes. So here you can see that in for sigma equal to 0.5, we get the delta x is 0.27. The spreading is less. For sigma equal to 1 I think, you know, 0.5, 1 and 2. So for sigma equal to 1, the spreading is little bit more than sigma equal to 0.5, and the last one is sigma equal to 2. The spreadings are more. Okay, so after getting this graph, you can easily understand in position space, the positional uncertainty is increases as sigma increases. So Heisenberg predicts, or the Heisenberg uncertainty principle tells us that if we Fourier transform this and we shift it into momentum space, then we will get the reverse effect of this. That means here we get the less uncertainty of measuring momentum, and here the more uncertainty, or little bit more uncertainty if we may measure the momentum. Now it's time for plotting the momentum uncertainty. Okay, so I'm just copy pasting it for momentum space because I'm very much afraid of a spelling mistake. Okay, so plot k and shy k, just change that position to momentum coordinate. Okay, so just copy paste this one also, control C, control V, just change that position space leveling to momentum space. Here delta x is delta p, and here is also delta p. Okay, so put it this way. So yes, okay, hope it will work. And the last one is this comment for plotting. Ah, sorry. Oh, I think I have to change this coordinate also. It is 1. In subplot it is in 1 position. So if we run it, hope it will work. Yeah, yes, it works. So I have to some refine this chart for better understanding. For that I have to exit from this for loop. Okay, and I have to do plot plt dot tight, tight, tight layout uh, and plt dot show. I think now it will be more clear. Yes, 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 yes. Okay, so this is our result actually. So now you can see that in position space, the measuring of positional uncertainty is 0.27, while in momentum space, if we Fourier transform this, then the measuring of positional uncertainty is 1.06, and if we multiply this del x into delta p, it is coming like 0.28, and it is 0.14, it is 0.07. And you can understand, see here the delta x is increasing, and here the delta p, the trend is decreasing. So that's it, that's how you can visualize the Heisenberg's uncertainty principle. So that's it for today.